if you're in physics. So we'll go with that one. It's also known as one of the basis vectors. We could have another basis vector, but let's not. Let's try another vector. So can you guys throw out 3 numbers? 3, 7, 10. Wow, that's going to get big. 3, 5, 7. Let's go negative.
What section are we talking about?
We're still, what was the last thing we did? 1, 3? Yeah, so this is kind of touching on 1, 3 and then kind of getting into 1, 4 a little bit. Negative 8? Let's get something smaller. Negative 3, negative 2. Let's go negative 2. All right. So my plotter over here allows me to draw out vectors as well. So I'm going to draw out these vectors that we have, that we've chosen. Of course, the vector, let's draw the vector in red. That's 0, 0, 1. And then let's add another vector here. And that vector was 3, 5, negative 2. Let's draw this in red. Also red, green. So it's big, so we need to zoom out a little bit. If we want the space spanned by these 2 vectors, what we're essentially doing is we're scalar multiplying this and we're adding them. So it turns out that in Calc 3 there is this idea of a parametric surface, which is what we're going to do. We're going to create a parametric surface. And I'm not going to tell you very much about it, but all I can tell you is that if we take that first vector and multiply it by a scalar, and we take the second vector and multiply it by a scalar, and then we let those scalars be whatever we want, we can actually let those scalars be some parameters. Now, in most programs, they call it S and T. T is your parameter for usual parameter, and S is the letter before it. But in some programs, they require you to use different variables. So in this case, they're using U and V. So I'm going to take a look at my X components of the vectors, and I'm going to say I'm going to multiply my first component of the first vector by U, and then add it to the multiple of the second component times the parameter V. So do you see where 0 and 3 came from? They are the first components of those 2 vectors. And that's the X value. So the Y value of these vectors would be 0 plus 5V. And I'm not going to put the 0 there anymore. And then the last one is going to be 1 times U plus, or I'll say minus 2 times V. Okay? Now, if I simply go 0 and 1, if I let this to go from 0 to 1, and I'm going to plot out this graph, anybody know what I'm going to get? Any guesses? The vectors we already have, but I'm actually going to get a surface here. So using those vectors that we already have, what do you think, what surface are we going to get? A plane that contains both vectors. But since I'm letting my scalar go from 0 to 1 only, this plane isn't going to go on forever. What's that thing called? It's going to be a parallelogram. It's going to be a 2-dimensional parallelogram in 3-dimensional space, and that parallelogram will be on the plane. Thank you. So let me just graph this, and then oh. A few more people here. Caesar, Evan, it's all in your row. Graph? It didn't graph anything. What happened? Oh, maybe we'll put 2 steps here. No, what happened? What's going on? Oh, I have to click. There it is. We'll stick with 1 and see. So this is that parallelogram that they have, right? Now, if I go extend this, remember these scalars u and v can be anything we want. So we can extend this to, let's go to 3 for now. And then the number of steps allows us to cut it up accordingly. So the thing is that if I match this up, it'll, I don't know if you guys will understand what I'm talking about, but it'll stay like whole numbers, so you can see a grid. It's probably too big to see now. Maybe we'll change the color of this vector.
So instead of changing the original vectors to achieve the same thing, you have these u and v's to be scalars.
You have the u's and v's to be scalars. Yeah, so the u and v are like the scalars. You know the A1, A2, A3 business? So those are u and v's. So that means the span of these 2 vectors would be anything on this plane. And then you can see, I purposely set this up so that you can see the grid marks. You can see the little parallelograms or rectangular things. It's actually parallelograms that are broken up over here. And in fact, I can, let me set this up so that it goes from minus 10 to 10 with steps of 20, minus 10 to 10 with steps of 20. So now it's this plane that contains those 2 vectors, and then each of these things would be, each point on this plane is a linear combination of those 2 vectors that we're looking at. Does that visual make sense so far?
Point is a linear combination.
Each point on the plane can be written as a linear combination
With scalars of the original vectors?
with scalars, the original vectors being scaled.
With, like not the same. Okay.
So let's do this. Let's get a span, or let's get a point that we know that's going to be on this vector. Okay. In other words, maybe give me 2 numbers here so that we're going to get a nice number here. So kind of reasonably small, positive or negative. What? No, not 0. I mean, we could have 0 here. 1, and then here? Negative. Let's do negative 2. All right, so what's this going to be? Minus 6? Minus 10?
No, plus 5.
Plus 5?
Negative 2 times negative 2 is positive 4. Positive 4 plus 1.
Okay. So let's ask ourselves, is the point minus 6, minus 10, and 5 in the span? The answer is yes, because we know that these 2 numbers are. And actually, we can even go further than that. Say we know where this point is based on these 2 numbers that we have. We're going to go follow these vectors, and this first vector is being multiplied by 1, so I'm just going to keep the same orientation. And then now I'm focused on this line right here, because that line has all the points where the scalar multiple of this is 1. And then I'm going to go -2 times this vector. So this is the positive direction of that vector. I'm going to go -1, -2. So I'm going to be at this point right here. I should be. Okay? So if I plot this as a point, this is -6, -10, and +5. Now let's make this, what color should we make it? Purple. You can see that vector right there goes up 1, and then -2 of these grid marks opposite of this vector right here. See how we got there? So any point in here, even a space in between here, we can get to that point. Right? So let's say if I take this and multiply this by 1, 2, 3, 4, 4.5, and then I take this vector and multiply it 1, 2, 3, 3.5.
It's hard to see the.
Oh, 1, 2, 3. Yeah, so 2.5. Then I would be at this point on the plane. And that's a point on the plane. Right?
Right.
So that point is on a plane. Now just give me another random point. Give me another random point.
You say in the span, because you pick a point within your domain range.
Yeah. Well, within.
Otherwise, we'd say in the plane.
Say it again.
If the point in the span, only because it fits the domain, otherwise we could ask if the point in the plane. Right?
Well, saying that it's in the span in this particular example is saying it's also on the plane.
So the span that the vectors make is a plane, it's the entire plane.
For this example, if we have two vectors in 3 dimensions in R3, then it's the plane. And then it's a plane.
The span is the same as the plane.
The span is the same as the plane, yeah.
So then we can have more than 2 vectors in additional dimension, and then we can have something other than a plane.
Correct.
Span,
Yeah.
Whatever they make.
Yes.
Generally infinite,
Yeah.
usually.
Yeah. Because remember, these numbers over here, you can have as anything. You can have any numbers going from -infinity to +infinity. So there's a million infinite number of choices. All right, now we randomly took this vector, took this point, and we know that that's not on the plane. So the question is there any way negative? The question is, are there any points that we can put in here so that we can get this to equal to -7, 8, and -9? The answer is no. We'll see in the next section that we're going to do how we're going to do this, right? And we're going to use a matrix. Oh, I need to use my other computer because some letters don't work. So we need to solve the equation that has these matrices on it. So we'll call it x sub 1. That's minus so we generally want to solve for this system to see if we're going to get a solution. And then the answer for this is going to be that we're not going to be able to find anything. Okay, and we'll look at an example to do that. So the space spanned by these two vectors can be a plane, and I'm taking screenshots and stuff like that because I'll put it as part of our notes. In addition to the notes that we're going to have today. And then is that point part of the plane? I guess I should have taken that. And then we actually did our little math over here where it's 1 times 0, 0, 1 plus negative 2 times, what was the second vector? 3, 5, negative 2. And then that is a linear combination that gave us that point in space, or in space that's in a plane. And then we got this last one where we didn't have the span, and that's because that point was not on the plane. I don't know if you guys noticed, that point's sitting over here. Right here. So graphically, we have the point out here, not on the plane. Okay, so we can't get to that. So if we were trying to solve for this equation, we will not get a solution. Okay? All right, so hopefully that helps a little bit with visualizing this. If not, try to look over the video again and slow it down for yourselves and try to imagine how this would look like. And this is a special case because we're looking at a span of two vectors in 3 dimensions, and that's a plane in 3D. The span of one vector in 2 dimensions is a line in 2D, and then so depending on how many vectors you have and then what your Rn is will depend on what kind of object that is. All right, so we'll pause this idea for now. I need you to understand this idea because we're going to keep coming back to it. This is going to be our hands-on visual example that we can always view if we need to. When we start talking about basis vectors and spans and linear independence, this is going to be important for us. Okay, now we're going to jump to the new section that we have that's related to this, and you can see, look at the matrix equation here and imagine how that would relate to what we were just doing. All right, 1.4. So here we have a definition and the product of an M by N matrix, and then here A are column vectors. So I know A over here looks like a row vector, but you have to look at A, little lowercase a, each of them as column vectors. So really, this is a square matrix instead of just a row matrix. So if A is an m by n matrix with columns A1 through AN, n is the number of columns, and then x, vector x, is in Rn, and then the product of A times x is denoted by AX, is a linear combination of columns of A using the corresponding entries in X as weights. So you're essentially writing out a linear combination. When we say linear combination, we got to think of addition or subtraction, addition and scalar multiplication. So you have a vector, you scale it, and you add it to the next vector scaled, and next vector scaled. So that whole idea of scaling a vector, when we say we scale a vector, we're multiplying it by some scalar, and that's what they mean by weights. It is kind of like taking a dot product. This looks like a dot product, except that these are not just regular numbers. These are actually vectors.
Oh.
These are vectors.
Vector of vectors?
So these are vectors. Yeah. In fact, how many elements are in A? Try it again. How many elements are in A? M and N sound the same. M&Ms. M&Ns. Each vector A has M elements in it. And there are N vectors. This is how you get an M row and N column matrix. Okay? So AX is defined only if the number of columns of A equals to the number of entries in X. So you have to match the number of entries in X with the number of vectors that you have.
X here is a scalar.
This X is a vector, and the vector X is represented by this vector x1, x2, x all the way up to xn. Those are the components of your vector X.
What I was saying with the dot product was, if we were to expand the vector of, or the matrix A out into a matrix instead of a vector of vectors, then it would be like you're taking the dot product of the vector X, which with every row, and the dot product of every row becomes an entry.
Yeah, that works too. Yeah. So each of these, so then you'll have essentially M expressions. Okay?
So what is A? Capital A?
Capital A is a matrix.
So vectors.
Yeah. It's a matrix of vectors. Okay. Let me squeeze in an example, precisely the example that we were working on. So let's let A1 equal to 0, 0, 1. and A2 equal to 3, 5, negative 2. And then X, how many components should X have in our example? In our example, X should have 2 components. Because, remember, I only have 2 vectors here. And the number of vectors needs to be the same as the number of components you have for X. Okay? And so your matrix A in this case is going to be a 3 by 2, so 0, 0, 1 for the first column, and 3, 5, negative 2 for the second column. And then you're going to multiply that by x2. What are you going to get? You're going to get x1 times 0, 0, 1 plus x2 times 3, 5, negative 2. Right? So that's the AX part. And then we're going to set it equal to B. And then we're going to see if we can find a solution. All right? Does that make sense? Yeah?
So you mentioned we can think of vectors as points.
Yes.
So you have 0, 0, 1, and then you have this other vector.
Mm-hmm.
And then we're talking about x1 and x2, which is a two-dimensional vector.
No, x1 and x2, yes. So you can think about x1, x2 as a two-dimensional vector that, in this case, is not represented geometrically. x1 and x2, go ahead.
So are we trying to convert x1 and x2 into that other thing?
No.
Or all values in x1 and x2?
Not quite. We're trying to find x1 and x2. In this case, the x vector is not geometrically represented in our drawings. Okay? The x vector that we have, x1 and x2, happen to be the scalars that we would need to multiply the first and second vectors by to get to that point.
What point?
To get to the whatever b that we have. We haven't. This is this is the b vector that we haven't gotten to yet. But yeah, that's to get to this point. Now, in our first example, we had 1 and negative 2 that would get us to that point. And our second example, where the point was not on the plane, there's no values for x1 and x2 that would help us get to the b point. Okay, and we'll get there in a minute. Yeah.
Is it how we multiply two matrices? The first and the second, like the first column of the first matrix and then first row of the second one?
Well, the whole matrix multiplication business is not quite there yet. So Evan mentioned the thing that this kind of looks like a dot product, and the dot product idea here kind of makes sense, but it also, what you're dotting here is you're dotting one element with not another element, but an actual vector. And so the matrix multiplication business is not, we're not there yet. Yeah.
Another vector.
This here will yield a vector. The matrix A times a vector X will yield another vector. And you can only do that if you're matching, yeah, if it's defined. If you're, if your vector has n elements and your matrix has n rows. They have to have the same number. Columns, sorry, n columns. Okay, so what I'll do is in green, I'll try to walk us along with the example that we did at the beginning of this class as we're trying to find out more information about the ideas in this section.
Say that the number of columns A has to be equal to the number of entries in X, but there's 2 entries in X. Answer my question.
Okay? All right.
Yeah, I got it.
Good. All right. Yeah.
Is it okay if you put the x1 and x2 before the vector?
No. The order is important. So the matrix goes first. The matrix is on the left, the vector is on the right. So that's a good question. The order matters. We've been dealing with commutative law where we can change the order when we're adding or multiplying. We've always done that. With matrices, we cannot do that anymore. Okay, the order is important. All right. So here's an example that they have. They have V1, V2, V3 vectors in Rm. Write a linear combination of this thing as a matrix times a vector. So this is kind of like similar to what we did. The linear combination in vector form of 3v1 minus 5v2 plus 7v3 can be written where the v1, v2, and v3 are vectors. Now, they don't specify what m is equal to in this case. But we know the n that they used is 3. And there's 3 columns for this matrix. And there's 3 elements in our vector. That has to match. The number of columns.
No, I mean the 3 and 5, 7. Oh, sorry.
No. So we don't know what these vectors are.
Well, just, right. Send it to right scalar, then vector, up over here. So it looks like it would make more sense if they did the same there.
Because this is AX, so this is when the matrix is A.
Yeah, so the matrix A, this is the matrix A right here.
Oh, okay, okay.
And this is the vector X. Okay, see how that relates to our example, right?
Okay.
The matrix A are made up of these column vectors, and then the vector X would be multiplied on the right side of it. Okay, so this is just a quick example that they have. Again, we haven't gotten to B yet. Putting B there will make it a little bit more interesting for us. All right, now let's go back to the idea of systems because that's what we've been dealing with. Now let's write the system of linear equations as a vector equation involving a linear combination of the vectors. So if we remember how to write a system into a matrix of coefficients, what we can do is we can make your matrix of coefficient. Let me just take a peek here. Yeah, they put the matrix of coefficients in the next one. But just imagine the matrix of coefficients here as a 1, 2, -1 in the first row. And then if we augment it, the augmented part will have a 4. And then here, the coefficient of x1 is 0. And then we take a look at the coefficients of the rest. So what we're saying is that there's really this deep relationship between the vector form and the matrix. And if we just focus on the vectors here, these columns of the matrix will end up being your vectors that you would write in vector form. Not really. Factorizing is another topic. Factoring, 6 is equal to 2 times 3. That business is splitting up a number, and
you have a vector here, and you're trying to say, can you break it down into a linear combination? And you have,
yeah,
you're trying to kind of break apart the scalars from the standard.
yeah.
The most basic.
I see what you're saying. So, yeah, so what you're doing is you're peeling apart the matrix
From the
but
scalars.
from the scalars to the vectors.
To the
Yeah,
vector you care about.
right. But I want to be careful with the word factorizing because we're going to have a whole slew of factorization techniques later on.
I was just wondering if another way to think about it is it relates to span. It's like, does the span of these three vectors include the B vector or not?
Yes, that's exactly what we're going to go to.
Because it's a linear combination.
Right. So the question is, if we can identify these column vectors as vectors on their own, the question is, there's a span of these three vectors going to include this B vector, which is the same question that we started with today. Okay? But this is slightly different because now, where are we? Where do we live in these vectors? Where do these vectors live?
Span.
Yeah. So we're in R2. These vectors are in R2, right? Because if you look at each of these vectors, they only have 2 components. I mean, there's 3 of them, but they just live in R2. Okay? All right. So now, this is where we can rewrite our matrix into this. Remember that this is just a coefficient matrix. And this is what they're calling our matrix A. Again, notice the columns. Those are the vectors that we were looking at earlier. Now, your vector X has 3 components because we were looking at 3 matrices. And then this is where we introduce our B. Okay? So this is called a matrix equation. When you can write it as a matrix. Matrix times vector equals to another vector. And usually this is the vector that's unknown. Okay? All right, now here's the theory behind it. If you have an m by n matrix with n column vectors, by the way, each of these column vectors, AI, have you guys seen that symbol? That little e, epsilon? That says it's an element. It just tells us where it lives. And this is an m by n matrix, so each vector here has m components. And there are n of them. So if A is an m by n matrix with columns A1 through AN, and B is another vector in Rn, then the matrix equation has the same solution set as this system of linear equations, or the vector equation that we've been talking about.
We can find these PowerPoints on the Canvas site.
Yes. No, it would be in the My Math Lab.
Oh, how do you find it in there?
What is it?
That's someone else.
Multimedia library.
Oh.
Multimedia library. I think there's an error here. X is in Rn. B is in Rm. So, if you guys downloaded the PowerPoint presentations, I think they have a typo. So Mx should be in Rn, and B should be in Rm. Because B has to have the same number of components as the column vectors. Okay? All right. So what they're saying here is that whether you're dealing with a matrix equation, a vector equation, or whether you're trying to reduce an augmented matrix and solving for that augmented matrix, it's all the same thing. That's what this theorem is saying. All the same thing. Okay. And then it's also saying that it has a solution if and only if B is a linear combination of A. So this is the idea of a linear combination now. And that relates back to this vector equation. They're saying B, the vector B, is a linear combination of these column vectors. A1, A2, all the way up to AN are all column vectors. So if it's a linear combination of all those column vectors, then we can solve for x1, x2, x3. And if it's not, then you're not going to find a solution. All right, here's another theorem that says that each of these are equivalent, which means if one is true, then the others are true. But if one is false, then all the others are false. So it's all true or all false. So for each B in Rm, the equation AX equals B has a solution. If that's true, then each B in Rm is a linear combination of the column vectors in A. And if that's true, the column A span all of Rm. And if that's true, then A has a pivot position in every row. So no free variables. No, they could have free variables.
Oh, okay.
Okay. So this is a matrix equation. It's a linear combination of the column vectors. So this relates our matrix equation with the vector equation. And the vector equation, remember, it's a linear combination, so it's x1 times a vector plus x2 times a vector plus all that stuff. And all that stuff is equal to b, so that's your vector equation. And the columns of A span this, so this is saying this is your matrix A, or augmented matrix. So this talks to the augmented matrix, and then A has a pivot position in every row that also is looking at a matrix.
When we say matrix A augmented, you mean
The augmented matrix A, I guess that should be down here. Well, both of them is dealing with the matrix A. And then if your row reduced to matrix A, then the augmented part is saying that if we put B on the last part of it, on the last column, then we can have solutions for it.
Okay, when you say B, you're talking about the matrix equation?
Yeah, part of the matrix equation also coming from the vector equation. Actually, I don't know if C and D deal with the augmented part. Let me scratch that out. Because I think this just deals with the matrix itself. Yeah, let's scratch out the augmented part. All right. Now they have this example here, but I think what I want to do is I want to skip to this one and talk a little bit about some of the theory, and then do the example that we started, and then if we have time we'll come back and do this example that's given here. So I just want to introduce the idea of the identity matrix. So if you have your augmented matrix, and then you're able to get the identity matrix for the first part, and then the augmented part is going to be some whatever values, that would be, you would get to the identity matrix by doing the reduced row echelon. So if you do the reduced row echelon form, remember that the leading coefficients or the leading pivot points are going to be 1, and then you would have 0 in each of the other elements in each of the columns. And if you happen to get the identity matrix, then you're well on your way to being able to solve for this. So that's the identity matrix. And then a couple of other properties. The property that the matrix times the sum of two vectors can be distributed, and then a matrix times a scalar multiple of a vector can be associative. Okay, so these two are a couple of properties that we might run into later on that would be good to deal with. Okay? All right, so let's go back to our example. The rest of this PowerPoint presentation proves those properties. So let's go back to our example where we have an equation already set up here for us. Let's do the example that we already know the solution to. So, remember what it was? What was that first number that we got? That was -6, -10, and +5. So this is your vector equation, right? And then we can rewrite this as, right now this is a linear combination of those vectors. We can write this as, let's see, this is x1, a1 plus x2, a2 equals b. Now we can rewrite this as a matrix. In matrix form. And then we can try to solve for this. If we write it as an augmented matrix. Right? So let's solve for this. I probably want to switch the first row with the third row so that this could be on top. So I'm going to show my elementary row operations in this example. Right? And then for the next step, I probably want to, let's just do one quick simple step over here. Multiply the second row by 1/5. And then I'll take the second row, multiply that by -3, and add it to the third row. And I happen to have gotten rid of all of the third row. And I can get rid of make this into a 0 as well if I want to. So I'll take the second row, multiply it by 2, and then add it to the first row. And this is going to be 1. And this is going to be -2. Right? So we have the solutions that we got, which is x1 is equal to 1, x2 is equal to -2. And that's what we got. Now, if you try solving for this equation, you'll see that you're not going to get a solution. Okay, so we won't finish this. I'll let you work it out and show that it's not going to come up with a solution. And then And then next time we'll dive into 1.5.